Hey folks, welcome back to another video on this series on quick paper summaries. So this week I've got like three papers that I want to quickly go over. So let's jump right in. So the first one is this one. Wait, we don't need to wait. Removing thinking tokens improves reasoning efficiency. So if you've seen, right now there's a trend of all these reasoning models like DeepSeek R1 and ChatGPT, DeepThink, and so on. Especially with the Chinese models, they have a tendency to so there would be, if you've seen their chain of thought, you would see a lot of weights. So a model will go down a chain of thought and then it'll be weight and it'll self-correct itself. Sometimes there are too many weights, sometimes it'll get stuck in a self-correction loop. So weight keyword is a way for the model to just backtrack. And you see a lot of excessive weights in the DeepSeek R1 style. So in this paper, what they do, I believe this is just an inference time trick. They suppress the weight tokens. So what they do is during decoding, they suppress. They don't output weight and a bunch of other keywords like and they'll just like output the next highest probability one. And that seems to just suppressing these keywords, these um, directional changing keywords. It boosts performance, and you can you can see once you have this data, you can use this data on use it as SFT or put it in pre-training to reduce this this backtracking behavior, because that's what a lot of reasoning models suffer from, excessive backtracking and driven by these weight tokens. And here they say, you know what, just suppress them and the model will do better. So, it's a simple, interesting paper. All right, moving on to a cool paper, which is something really fascinating. And this is something that I've been thinking about for a bit, and these guys just went and implemented it. So pretty cool. Um, so, so here they do attention over 3 tokens. So the typical attention is between 2 tokens, right? You have a query token, you have a key token. So it is measuring um, order 2 behavior or order 2 correlation. But what if you could add a third one, like do an order 3 correlation? And this is what this paper is, like somehow like get, so you have a query key and a third key kind of like correlation. And the way, I'll quickly just jump over this paper. It's pretty simple. Implementation wise, it's pretty simple. The way they do it is, so we create a query matrix, or rather a query vector, a key vector, and a v vector. And then because now we are doing not just like 2-point attention, we're doing 3-point attention. They produce a new key and v representation. So the way they compute now the attentions is it is a three-way inner product, so between q, k, and the k prime. So obviously this thing has 3 indices, and then the normalization thing is fine. And when you have 3 indices, now what you do, so typically you just have 2, you compute the inner product, and then you multiply with the value matrices, and then you get your the new representation for I. Here now we'll have to do it with the Hadamard product of 2 values, because now we have 1 extra in this that we need to contract. So so once you have the attention scores, now the attention tensor, instead of being a 2D tensor, is a 3D tensor. So to contract it, we need to multiply with 2 sets of values, and this is what they do. So now, as you can see, this will be computationally challenging. So the rest of the paper is dedicated on how they implement it in like efficiently using a Triton kernel. And they also show that this as you scale up, this shows better behavior. So across at least the 4 benchmarks that they considered, it starts performing better. And you can see, right, like because attention is 2-point, like attention is the simplest thing. The more complexity you add, the better things will perform. I wonder, so this 3-point attention is obviously like a subleading effect. So I wonder if we could do something like you have a standard attention, and then you have these subleading effects um, together. Like, so you have the standard attention with full loss and the subleading attention in a few layers or something like that. So I think there's a lot to do here, but yeah, I thought that was cool, so I thought I'd share it with you guys. Um, this I mean this obviously this thing can be generalized to like multi-dimensional attention. Right now, they only do it to like one more point. Okay, and then finally we have this mixture of recursion. So a few weeks, or rather a long time back, I reviewed a paper where the key insight or scaling that was done was by doing recursive loops. So let's say you have a transformer block. In the middle 4 layers, instead of just passing it to the final layer, you loop over the middle layers a bunch of times, and then you pass it to the final layer. So this way, you're scaling in the compute dimension, not in the token space. And that paper was at a sequence level, but here what they do this recursion at a token level. So here's the kind of rough overview. A number comes in, or whatever the input comes in, and then for layer 1 to whatever layers, the token either passes through or it is recurred a bunch of times via these layers. So here, this is a not such a clear diagram, but this is a better one. So some tokens just pass through, other tokens recur a bunch of times. And this is an even better figure where you can see in a sequence, the first token is processed a bunch of times, while the second, third, fourth, and so on are processed only like one time. Some other ones are recurred a bunch of times. So this is a more efficient way of doing the same thing. And the way these guys do it is, so the way they do it, so they have like 2 ways of deciding, a token choice routing and an expert choice routing, kind of similar, but the main idea is that, so let's say we have 3 iterations, like, so I could loop it once, twice, thrice. I have a router that classifies how many of these tokens will go into loop 1, and then let's say only these ones go into, you know, the after the first loop, they go for second loop. So at every order, I will only select from the remaining ones. So these tokens, so the one that just went through 1 iterations and no more, will just pass through. The other ones will take part in this routing decision. Hey, do we need to loop twice? And then finally, whatever's remaining will go through. So for example, we picked these 3, then only these 3 will go into the attention module or recurring thrice. For all the other states, we probably take the frozen value from the previous loops, but that's the rough idea. That's a simpler way of doing it is token choice routing, where each token is classified. Hey, I need to be routed once. This one gets, hey, I need to be routed twice. That's why you get loop 1, loop 2, and the third one, hey, I need to be routed like 3 times. So you make, just like an MOE, you make a routing level call, how many times your token will be recursed, and so basically, the tokens that will be recursed will be passed through an attention module. They will see all of the tokens, but they will see past representations of other tokens if the other tokens did not participate in this recurrence. So that's the basic idea. This is basically like a fine granularity level analysis. But my biggest concern is that they didn't scale up to larger models. And in larger models, you start seeing behaviors which you don't see in smaller modules. So I'm not sure, like, I'll take their results with a grain of salt. But it's interesting. Like, so they went into depth about these architectural choices and all the different things. So, an interesting paper. And I'm quite interested in this recursion, like self-recursion loops in models. This is a nice new paradigm of scaling. Yeah, so I think that's about it for this video. I'll see you guys next time. Cheers.